All right, let's take a look at this equation known as the heat equation. See how it might be useful in our calculations. Notice in this equation that we have four variables. The first one, Q, stands for the quantity of heat. So Q for quantity of heat. That's going to be measured sometimes in calories. More often in a physics class, we'll measure that in joules. The M you've seen before stands for mass. So the mass of the object that is being heated. The delta T comes as a package. This is a unit. So delta means change in and T is temperature. So let's just call this the temperature change. We'll look at how you can calculate temperature changes. And then this variable in the middle is maybe a new one to you. It's called the specific heat capacity. Specific heat capacity is a way that we measure how well materials can absorb or release heat. Specific heat capacity. To find out a specific heat capacity, oftentimes that just means we find a table that lists a bunch of specific heat capacities and read it off the table. So if we have that available to us, it's quite useful. Notice the units are kind of funky on those. Let's try answering a question then. We'll use that equation to answer this question. How much heat is delivered to this iron block? This iron block in this problem has a mass that is 2.0 kilograms. We'll record that. It's iron, so let's just run over here real quick and find what is the specific heat capacity for iron. Iron is 450 joules per kilogram degree Celsius. So I'll write that down. Let's see. C, 450 joules per kilogram degree Celsius. The temperature change. Let's look at how you find temperature changes. So when you're finding the change of anything, it's always the final minus the initial. So for this, we'll take the final temperature, subtract the initial temperature, and get 195 minus 35, and that would give us 160 degrees Celsius. All right, I think we have everything we need to calculate the heat. So heat, or Q, equals the product of MC and delta T. So we would say 2 kilograms times 450 joules per kilogram degrees Celsius. Multiply that by the temperature change of 160 degrees Celsius. A little bit of magic happens here when the kilograms cross out and the degrees Celsius also cross out. So when you multiply kilograms times per kilograms, they cancel. Handy. So that leaves us with units of joules. And if you punch those in your calculator, it leaves you with an answer of 144,000 joules. Might write that as 144 kilojoules if you don't want to write so many zeros. All right, that's how we calculate the heat that is gained in this case by a chunk of iron. Let's try one more. It says if I applied the same amount of heat, that's 144,000 joules of heat to this block. This block is the same mass. It's also 2 kilograms. But this is a cylinder of aluminum instead of a chunk of iron. So let's look up the specific heat capacity for aluminum, and I'll put a little AL there so I remember. This one's for aluminum. I see aluminum in this table is listed at 895 joules per kilogram. 895. It's a little bit more. Per kilogram degree Celsius. And so in this calculation, they're asking us to find the final temperature. We already know the initial temperature, so we got to find the final temperature. We can plug this into our same equation, Q equals MC delta T. We can find delta T, and then from there we'll calculate the final temperature. Let's do it that way. So 144,000 joules equals 2 kilograms times 895 joules per kilogram degree Celsius times delta T. I'm going to leave the variable in since I don't know the value. And of course, the next step is to divide both sides by that 895 and that 2 kilograms. And when we do that, 895, we will be left with just delta T. So over on this side, I'm going to write in a 2 kilograms and an 895 joules per kilogram, degrees Celsius. And we can cancel a few things out here. Those are gone. Those are gone. Some units will cancel, joules over joules. And then these kilograms and these per kilograms canceled. So when I do the math, which I will in just a second, I will know the value for delta T. And I know the units are going to be the units that didn't cancel. They're 1 over degrees Celsius. We just write it this way. So to figure that out, we need to divide 144,000 by 2 and also by 895. And that gives me a value of 80. I'll keep one more digit, 80.4. 80.4 is the temperature change. Now recall that delta T, or temperature change, is the final minus the initial. So I know that it changed by 80.4. And I also know the initial temperature. It started out at 35 degrees Celsius. Don't know why I have parentheses. Don't need those. Okay. Let's do a little more math here. I got to add 35 to both sides. Adding 35 degrees Celsius will cancel them from here. And we'll just have to add a little 35 degrees right in there. And that gives me a final temperature of 35 plus 80, let's call that 115. I don't really get to keep to the 10th place here. I think we stop right there, and that'll do it. Final temperature, 115 degrees Celsius. Interesting. Just want to point something out real quick. Everything was the same over here, but the iron got up to 195 degrees Celsius. Starting with the same mass and at the same temperature, this one only got up to 115 degrees Celsius. What's going on? Well, as we said before, specific heat capacity tells you how well something absorbs heat. Aluminum absorbs heat better or with a less of a temperature change than iron did. Now, if you look at this table, you could see water does an even better job. It absorbs heat with little temperature change, better than any other thing on this list. So much better, actually. What does that mean? That means water's a great material to use if you're trying to keep the temperature from increasing too much. Okay, our last calculation says this 525 gram cube of ice loses 12,000 joules of energy as its temperature drops by 12 degrees Celsius. They want us to find the specific heat capacity for ice. We can do that if we write down a few things. We're going to use a formula that has specific heat capacity in it. We've used that formula already once or twice. Q equals MC delta T. I'm going to do some magic on this formula. Before I plug in numbers and make it difficult to move things around, how about if we solve our formula for the missing variable? We're looking for specific heat capacity. Why don't we rearrange this? We'll solve it for specific heat capacity. That means let's get the M and the delta T over to the other side. We're going to divide both sides by M and delta T. Those will cancel, and we end up with this nice little equation that says specific heat capacity will equal Q divided by M delta T. Make a quick list of some variables. The M for this is 525 grams. That's a lot of mass. Delta, let's see, Q is given. Q, the heat. Heat, sometimes called energy, measured in joules. That would be 12,900 joules. And then finally, the temperature change. The temperature change, delta T. So if it says the temperature increases, or in this problem, the temperature drops, you recognize that's a temperature change. So temperature change here drops by 12. And you might be thinking, I'm pretty smart. and I know that this is dropping. That's a negative 12 degrees Celsius. That's great if you realize that. Now, if you're going to call that a temperature drop a negative, you should also call a heat loss a negative. So as it turns out, even if we label these both with negatives, the negatives are going to cancel out. All right, one other little detail before we plug this into our equation. Recall that in physics, we often work our problems not in grams, but in kilograms, and it might behoove us to go ahead and do that now. Let's just say 1,000 grams were a kilogram, because that's true. And let's divide 525 by 1,000 to turn that into kilograms, and we could write that number as 0.525 kilograms. I like that. C is equal to 12,900, negative if you want. But if you do that negative, you better do your delta T as a negative 12. I'm just going to use positives on both of those. And then for my mass, I'll plug that in as 0.525 kilograms. We like to cancel units out, but in this case, nothing cancels. That's all right. We'll just write all of the units then. All right, let's do a little dividing here. 12,900 divided by 0.525 divided by 12. That's going to give me a 2,047.6. Now, I can't keep all those digits. I can keep 2, so we call that 2,000. It's a little tricky to write that, 2,000 with 2 sig figs, so might be nice to write it in scientific notation with 2 significant digits. And we got to label that with some units, nothing canceled. So that's going to be joules per kilogram, degrees Celsius, just the unit we would expect if we were finding a specific heat. All right, hope this helps you solve some of your specific heat equation calculations.